Antimatter is the universe's reflection, a hidden counterpart to the ordinary matter that makes up stars, planets, and life itself. For every particle, there exists an antiparticle. Electrons have positrons, protons have antiprotons, and neutrons have antineutrons. These mirror particles share the same mass but carry opposite charges or quantum properties. When matter and antimatter meet, they annihilate in a burst of energy, converting mass entirely into photons or other particles, a process both violent and fundamental to physics. The existence of antimatter was first predicted by Paul Dirac in 1928 through equations that combined quantum mechanics with special relativity. His theory suggested that for every particle, there should exist a counterpart with identical mass but opposite charge. This prediction was confirmed a few years later with the discovery of the positron, the electron's antimatter twin, marking one of the most profound validations of theoretical physics. Since then, antimatter has become a crucial tool for exploring the laws of nature, testing symmetries, and probing the fundamental structure of the universe. Antimatter is extremely rare in the observable universe. While particles and antiparticles are created in equal amounts during high-energy events, such as in the early universe or in cosmic rays, an imbalance occurred in the first moments after the Big Bang, leaving a cosmos dominated by matter. Understanding why this asymmetry exists remains one of the deepest mysteries in physics. The weak force, through processes that violate CP symmetry, offers partial explanations, but the full picture of why antimatter is scarce and matter prevails continues to elude scientists. In laboratories, antimatter is created in tiny quantities using particle accelerators. Positrons are produced in radioactive decays, antiprotons are generated in high-energy collisions, and sophisticated traps can hold these antiparticles long enough to study their properties. These experiments allow scientists to test fundamental symmetries, measure magnetic moments, and explore how antimatter behaves under gravity. Some research even investigates whether antimatter could have subtle differences from matter, potentially shedding light on the universe's missing antimatter. Antimatter is not merely a laboratory curiosity, it also plays roles in astrophysics and medicine. In the cores of stars, positrons emerge in nuclear reactions and pair annihilation processes, contributing to energy transfer. Cosmic rays occasionally carry antiparticles across interstellar distances, providing natural laboratories for studying antimatter interactions. On Earth, positrons are used in medical imaging, particularly in positron emission tomography (PET) scans, where their annihilation with electrons produces detectable photons. Enabling detailed images of internal organs, the concept of antimatter also stretches our imagination. It challenges the notion of reality's uniqueness and forces us to consider a mirrored universe, one in which every particle has a twin that behaves oppositely yet shares the same mass and dynamics. Antimatter annihilation, while dangerous in theory due to the energy released, also hints at possibilities for futuristic energy sources, propulsion systems, and deep space exploration, where matter-antimatter reactions could provide unparalleled power. Contemplating antimatter is to confront the delicate balance of existence. It reminds us that the universe is not symmetrical in the simple sense and that the dominance of matter over antimatter is what allows galaxies, stars, planets, and life to exist. It shows that the smallest differences in fundamental processes can shape the fate of the cosmos and that the interplay of matter and antimatter underlies the most profound events in both quantum and cosmic history. In essence, antimatter is the mirror of reality, a reflection that illuminates the fundamental symmetries and asymmetries of the universe. It is both a tool and a mystery, a particle and its opposite, a fleeting presence with lasting implications. By studying antimatter, scientists explore the limits of physics, the early universe, and the deep principles that govern existence itself. Antimatter reminds us that reality is a delicate interplay of opposites. That even the invisible and rare can wield immense influence, and that the universe, at its core, is a complex dance between creation, annihilation, and energy.